All right, welcome back to the Vancast. We're gonna just review what we did last week at the end and just have one simple question, and then we'll come back to this pretty cool video from NASA. Okay, so let's get to the information I need to share with you. Shouldn't be long. Okay, so two things: review electromagnetic radiation. Using, not suing, we are not suing the sun, using the sun and answering one simple question. All right, so last week we talked a little bit about cosmic explosions and the information we can get from cosmic explosions, and we use electromagnetic radiation to do that. Okay, it's a kind of energy wave is what we said. And waves travel in waves. I know it's stupid, but that's it. Energy travels in waves. So water energy, sound energy, all of it travels in waves. And there's electromagnetic radiation, waves, a kind of energy wave. The little bit of that type we use as visible light. So anyway, so you can see here are waves, and really the type of wave and the amount of energy it comes from, it gives it the characteristic of a longer or shorter wavelength. And surprisingly, a shorter wavelength takes more power. You cannot create a short wavelength with less power. You need more power the shorter the wavelength. If you play with a rope, you'll see it's true. If you shake a rope slowly, it'll give you longer wavelengths. And if you shake a rope quickly with more energy, it'll give you shorter wavelengths. And you cannot get away from that. And then just how high they are, that's the kind of power for that wavelength, which is a little bit different. Okay, so the wavelength, that's the key. So we did that last week. So now I'm going to go to this graphic here, which will be available to us. Also, I have files. I can put files now into Teams. So this shows you different things about electromagnetic waves, which are a type of energy wave. So type of electromagnetic energy, it travels in waves. And this little graphic shows you a few little things. The most important thing is the size of the wavelength. So these longer wavelengths, which are radio waves, which are going through us all the time, these are less energetic. They have less energy. Okay, more energy is visible light that we see. It has this wavelength, medium-sized wavelength, I guess, on the electromagnetic energy scale. And then you get to more energetic ultraviolet. It's shorter. That's the stuff that can cause cancer for us. X-rays, which could be very dangerous. We don't get much of these short wavelength electromagnetic energy waves hitting us, getting through our atmosphere, because that would be a big problem. And then massive energy to make gamma rays. And luckily, those happen many light years away from us. Otherwise, we'd have a problem having life here. Okay, so those are the wavelengths. Okay, and remember, not one wave doesn't have different size wavelengths. One wave has either one of those types of wavelengths for the whole wave. Okay, so this is just giving you the size, a rough idea of the size of those wavelengths. Okay, frequency, we won't worry about that. That's like how many times, if you imagine a beach, how many times the waves hit the beach per second. So with the beach, it's more like 1 per second maybe, or something like that, 1. But with electromagnetic waves, when they're moving through space, by one spot, there would be many more waves moving through one spot in space. Okay, so that's frequency, and then the amount of the temperature, which is the amount of energy the source body can have to give off this type of electromagnetic wave. Okay, so these are more powerful, and you're looking at temperatures of 10 million degrees or more. This K stands for Kelvin. We won't worry about that. It's a very scientific measure of temperature. The increases are similar to what we know, Fahrenheit or Celsius. And then for these very long wavelengths, like to produce a radio wave, the temperature can be quite cool. Okay, so hopefully that explains this. Photon energy, you do not need to know that, but electromagnetic waves, including light waves, they're made of packets of energy called photons. They have no mass, but they're like a packet of energy, and they behave in ways we know how they behave, but we do not know why they behave the way they do. So the scientists that study that, when they start adding dimensions, like a universe with 7 dimensions, it kind of can start making more sense to them, apparently. So much of our universe is a real mystery. Really interesting to study if somebody was interested in that. So those are packets of energy. We don't need to know that. Okay, so let's look at this video looking at the sun in different wavelengths. So this is the same spots of the sun in different wavelengths. So the wavelengths, the higher the energy of the wavelength, which means the shorter the wavelength, generally involves a higher temperature also. So you'll be looking at different temperatures with these different wavelengths. And probably there's some atomic level characteristics you're observing too that I don't know enough. I don't know about. So probably there's more to it than just temperature. Okay, so you can look at this. More of the same. It's kind of cool. So these are different wavelengths which are associated with different temperatures. So you're able to observe different things. And some of these wavelengths you can see deeper inside the sun or outside of the surface in the atmosphere of the sun. Yeah, it has an atmosphere, the atmosphere of the sun. And also in the magnetosphere, the magnetic field of the sun. You can observe things better under different wavelengths. Okay, so I think that covers it enough, I hope. Now I need to get back. Okay, that should about do it. Space assignments. This file, you'll tick on the file. There's an icon on the top of Teams for files, and then you'll see it. Okay, so this is showing similar to what we saw. Looking at the sun, generally different wavelengths and different temperatures, which is good. So this wavelength, which is a longer wavelength, 4,500 Kelvin, and then as the wavelengths generally get shorter, 350,000 degrees Kelvin. As they generally get shorter, 200 angstrom, which is even shorter, 2 million degrees. And then this is the smallest wavelength, which has the highest energy, and a temperature of 6 million degrees Kelvin. This wavelength has a slightly higher, this wavelength is slightly more than this one. So still the energy level of what it's emitting must be more than this one, but they're talking about only temperature here. So, but still, they're both extremely tiny wavelengths, and you're talking about millions and millions of degrees. And you can see from the image that they're looking at different stuff at different temperatures. They're seeing different things as different parts of the sun are emitting different wavelengths due to different energy levels and different temperatures also. Okay, so that's kind of interesting. So all kinds of stuff going on in the sun. Really all kinds of interesting stuff. Okay, so that should be it today. Your question is very simply, when we observe the sun with different wavelengths, what else are we seeing that is different for each wavelength? So I'm hoping that is very easy. And we should be